So this is our first example of a zero knowledge proof. We proved that we know the secret key, and therefore we showed our identity. We proved our identity without revealing any information about our secret key. So the zero knowledge part of ZKP is not about the knowledge of the sender, because the sender obviously has the knowledge to generate the proof, but it's the receiver who gains no knowledge, no information about the secret that the sender has. And again, cryptocurrencies are mainly using this form of cryptography because they are interested in providing a trustless system much more often than privacy. And that was done obviously in Bitcoin. Then Ethereum came, and Ethereum was about creating an overall world computer. And Ethereum introduced the notion of a smart contract. So let's suppose that you have a smart contract. So a smart contract is basically a program, and a program that is executed by every participant in a node, and the success of the result of that program is then part of the state. So before with Bitcoin, the only program between codes was hard coded in the functioning of Bitcoin, and it was only about transferring coins between accounts or between addresses. Simplify a little bit, because in Bitcoin you also had the scripting language which allowed you to create some programs, but not very powerful one. With Ethereum, you had the entire possibility of what we call Turing-complete programs, which are essentially any kind of program that computers can execute today. So let's say that you have Ethereum smart contract that implements the rules of a Sudoku. So Sudoku is a popular game. It's just a puzzle game which has numbers, and your goal is to place the digits 1 to 9 in this grid, following a set of rules. The numbers should not repeat in the row and in the column and in the block. The exact rules are not very important to know. The only thing is that it's a fairly simple puzzle, in the sense that to write a program that verifies the correctness of the solution is not very hard, but actually coming up with a solution is known to be extremely complex in some cases. The real Sudoku is only 9 by 9, so computers can easily brute force a solution in a matter of milliseconds. But if you had the same rules with a much larger Sudoku, so instead of having 1 to 9, but you do 1 to 1 million, then it's much harder to compute the solution, to find a solution of a Sudoku, than to actually verify that the solution is correct. So we could imagine that you have a contract which presents this puzzle. So the puzzle will be a set of given digits in the grid, and you are challenging the puzzlers to come up with a solution. And if the solution is correct, you are going to transfer, the smart contract is going to transfer some rewards, some coins from the account of the smart contract to whoever provided the solution. All the computers in the Ethereum network will perform the verification. One of the core principles of cryptocurrencies, again, is that all the participants must agree on the same thing. Otherwise, what's the point of having a trustless system if there's no thing to trust? So that state is the one thing that has to be verified, and that every node has to agree on. So here the solution is either correct and the funds are paid, or the solution is incorrect and the solution is rejected. Since the solution is part of a transaction, like sent from one of the participants to the network, so we can say that transaction is either accepted if it's verified properly, or it's rejected if the solution is incorrect. So in sometimes, right, if you want to make it even more challenging for the system, you could say that you want to have verification of the solution, but you don't want to have the solution pushed into the system. And one of the reasons could be that once the funds are being paid, right, it's not really important to know the solution of the puzzle. Anyways, whoever has the has created the puzzle, knows the solution, and he could be publishing a solution in a different media, in a different channel, maybe online. But he should not have to record that solution in the blockchain. Knowing that the blockchain will be kept forever, it may not be very interesting to keep all these inputs, these solutions, when at the end of the day, all we care about was, okay, the solution was correct or not. So we have a situation here which should be a bit interesting, because we want to minimize the bloat, the amount of data that is stored in the blockchain, by omitting these solutions. But we still want to have verifiable proof, because there's no reason for node participants, if the solution is not provided in some form, there's no reason for the node participants to believe that that solution is correct. And you may recognize something similar to authentication before. Before, we have secret key as being the proof that you know something, or the solution to what plays the role of the solution in the Sudoku smart contract. But in the previous case, it was very obvious that you didn't want to reveal the solution, the secret key. Sorry. In this case, you don't want to reveal the solution, because really you shouldn't have to. But you can imagine other cases where actually revealing the solution publicly is not something that you want to do. Maybe you want to monetize the solution, and the solution has some intellectual property associated. So in this hypothetical case, we are saying that the verifiers are not interested in the solution, but they are very much interested in checking that the solution is correct. And that's where ZKP are really useful, because the beauty of the ZKP is that you can make them to show that you have a solution to any complex problem, not only problems where it's about having a number, having a secret key. So ZKP are much more general. You can make them match a particular problem, a particular complex problem, while keeping the properties that we have before about authentication. So again, it's about not showing the solution in any way that, even like partially, you don't bring any knowledge to the public, which could help that public or any person who can read your ZKP to reverse the process and find that secret information. And this is obviously very, very hard to prove. Proving that your proof has zero knowledge is very hard. Right? So this is why this entire field is extremely complex. Just the last point is the caveats. ZKP are fairly new in cryptography, and they've been studied for a few years only. That's very short compared to the time spent on studying encryption, hash functions, the other aspects of cryptography. But it's a very innovative and very important field, because the potential applications are very large. Some say limitless. But in my opinion, we are still experiencing the very early days. And it's similar to the 60s were for computers. Though the theory of computer science was mostly done or was finished, but at least didn't evolve very much since the 60s, we can say that today's computers are 100,000 times more powerful than the ones back then. So it's a bit similar for ZKP. The theory of ZKP now is we will see proving systems which they say they can do any complex problem. But the reason why we don't have one ZKP for everything is that they still have in practice different profiles, different properties, and we are going to talk about several different systems and what their advantages and disadvantages are. and why one cannot be used in every possible situation. But the thing is that in practice, it's very, very difficult to use, and it's very difficult to build a ZKP for a given problem. In the examples that you'll see and the tutorials you will see, some of them are very impressive because they compress a lot of information in cases where it seems like it's pure, it sounds like it's magical. But if you want to take a really real problem, for example, you want to create a new coin that has the property of encryption. So, for example, that's the case for Zcash. Or you have a coin that want to have a fixed size proof, blockchain proof, which is the case for Mina protocol. Then you see that there's really a lot of work that has to be put into the establishment of the statements that you are building the ZKP on, and the algorithms to create a ZKP. The thing is here that at the end of the day, cryptocurrencies are very practical, and the code that you're going to write is going to be executed by a multitude of machines. Therefore, the code that you have to write and the ZKP that you want to create has to be both quick to generate and also small in size. And these are very hard to get right now. Anyway, the goal of this series of videos is not to give you the exact information how to create these ZKPs, because again, it would take a really, really long time. And this would be like studying computers to the detail of being able to wire transistors and building from atomic operations, so from gates and stuff like that. So it's obviously super interesting, and if you are in the field of ZKP, that's what you are doing these days. But I'm guessing that if that's the level of detail you want to know, you would not be looking at this blog. All of this series is to gain a moderate understanding of what ZKP can do and how they can be built. It's, I think, still more than what you find on the other tutorials on YouTube and blogs, but it's not really at the level that would allow you to create ZKP systems and proving systems. I hope I'm wrong, and then actually one of you guys can do that. That would be obviously a great achievement for me. I would be very happy about that. But anyways, that's it for today. Let's end this overview here. And next time, we will start looking at some of the known usages of ZKP, so some of the applications in blockchains. So we're looking at several coins that are already using ZKPs in some ways, and that are already in production. So stay tuned for an overview of ZKP coins in the next video.